Okay, hello, and welcome to the last lecture on finite groups. We are still looking at representations. And what we're going to do in this lecture is try to give you an idea of the classification of irreducible representations. So, as we said in the last lecture, representations could be reducible or irreducible. And now we want to show you how to classify reducible representations. All right, let me start sharing screen. Okay, so here goes. So what are we going to do? As I said, we are going to classify reducible representations, and for this is going to be very important. So the thing that's going to be important here is something called characters, and so what is the character of a matrix representation? This object, character chi g, of this n-dimensional matrix representation GDG of an element G of the group big G is defined as the trace of the matrix DG. So it's very simply just chi G is going to be trace of DG. So it's just A equal to 1 to n dAA of G. So let's revisit this once more. So let's look at S3. And so if you look at this, then we saw that there were several sort of these elements, and we had a one-dimensional representation. We had sort of two one-dimensional representations that we said. There was so this was what was called a trivial representation, where everything was actually one. And then we had this, another representation where you would remember. So let me take you back to that. So yes. So this one was 1 for even permutations and -1 for odd permutations. So that is going to give you something else. Now, so you see that for these, even permutations, so these are just 1, but again, for the odd permutations, which were just these three objects, they're going to be -1. So it's a one-dimensional matrix. It's just the trace is going to be just as it is. Now remember, remember the two-dimensional representation, right? The two-dimensional representation, if I take you back, is going to be given by something like this. So these are, you can sort of figure out which one each of this is. So you see that the trace of these guys are -1. The trace of this is 0. So is this, and so is this. So so let's see what we get here. So if you go back here, then you will see that there is one. This is the one that gives you this particular thing is just 1 0 0. So this is this. So that gives you this 2. And 1 3 2 and 1 1 2 3 are represented by -1s, and we saw that the rest of them are 0. Okay. We can go to the three-dimensional word representation, and then we will see that it's 3 0 0 1 1 1. Okay. We can also go to the six-dimensional regular representation. There you'll find that this is 6 and the rest of them are zeros. We also did this, other thing where this WS was the equivalent representation, right? This was the equivalent representation that I told you about. Where did I say this? Let me try and remind you of what that was. So these two, yeah, I think it was somewhere. These were equivalent representations, and yes. So I showed you that this particular guy, it was S inverse d dw of S, and these were the matrices which we had, right? So here you see that this is 3, and the rest of them are as they are. So if you actually go back and look at the traces, you'll see that it's 3 0 0 1 1 1. So notice that this and this are identical, right? So the characters of chi w and chi ws are identical. This is because these things, as we said before, are equivalent. So remember, chi of some representation beta is a trace of the matrix, the trace of that matrix. And now what we have is S inverse. So this is, if we go on to something which is equivalent to it, this is, okay, remember that the trace has this cyclic property, right? So you can put in a 1 out here, and the 1 you can write as S inverse, right? Then d of beta. If you do that, and then you just move this around, so S inverse d of beta is equal to, so the trace of this is equal to trace of S inverse d beta of S. So this is this line. And now this guy, as you can very clearly see, is d of alpha, which is an equivalent representation. So if two representations d alpha and d beta are equal, that means necessarily that the chi's of these two representations, so the characters of these two representations, are one and the same. So as I again highlight, any two equivalent representations have the same character table, if you wish. Okay, so that's what this is. So there are going to be very many more interesting things, like the character of the identity is going to determine what the dimension of the representation is. Okay, um, so that's one more thing. And also you would find that if you have group elements that belongs to the same equivalence class, these are going to have the same same chi's. Now this is something that you can work out in a reasonably systematic way. So how do you do that? So chi of b and is trace of db. Now say db, so b is, say, g inverse ag. So this is these are b and a are going to be in the same equivalence class, right? So this is equal to this. Now you can split this up. D of g inverse ag is d of g inverse into d of a into d of g. Now you can use the cyclicity of the trace to actually bring this onto this side. So dA, G, dG, dG inverse here. Okay. And now again, you can recombine these two into d of G inverse. So d of the identity, that is going to be equal to the identity. So this is going to be just trace of dA, which is equal to chi a. So it just shows you that if these two elements b and a are of the same equivalence class, then the chi's that are I mean of these a's and b's would be equal. Okay, so the characters are then functions of equivalence classes. All right, moving on. So the another thing that you would want to look at here, if you go back here, is that if you sum up the thing here with the thing here, so if you add these two, then you're going to get this object. So let's do this. Let's see the first one. So 1 plus 2 is 3, so that holds. So 1 plus minus 1 is 0, which is great. Again, 1 plus minus 1 is 0. That's also great. Now you have 1, 0, and again 1, and 1, 0, and again 1, and also the last line. So you see that it seems that if you add this one and this one, you get this guy. Okay. So what is happening here? So the characters of the word representation are the sum of the uh, characters of the trivial representation D1 and the two-dimensional representation D2. So chi of W is equal to chi1 of G and chi2 of G. This is because d of w, as we have seen before, can be reduced to a direct sum of the trivial representation and the two-dimensional representation. So the traces of the matrices are the sums of the traces of the sub-matrices. Okay, this sort of gives us an idea of how a representation can be reduced. Okay, for example, it also suggests that if you were to look at the six-dimensional regular representation, this can be looked at as a sum over chi1 plus chi1 prime plus 2 times chi2. So this means that the 6 cross 6, this indicates that the 6 cross 6 representation can be split into the trivial one, the other one-dimensional one, and twice of the D2. So it would mean that you will have something which S and S inverse such that this goes into D1, D1 prime, and two of these D2s. Okay, this is something that you can explicitly see as well. So generally, the general lesson from this is so for the regular representation of some group, it is just going to mean that the chi of R is going to be the dimension of the irreducible representation, and the chi's of the irreducible representation. So this is something that happens for any group. For the identity operator, this particular thing has the very interesting. So this leads to this interesting formula that if you are looking at the identity in the regular representation, this is going to be the order of the group. And now if you split this up, so this is going to be the dimensionality of the irreducible representation times chi of the irreducible representation of the identity, which is again, this is just again f of this is again the dimensionality of the irreducible representation. So this is just sum over f of f irrep squared. For example, S3, as we have seen, has 6 elements, and is irreducible representations are 1, 1 prime, and 2. And so this has so as we saw so what is going to happen is that you can just very clearly see that if you put this in, then 6 here is going to be 1 squared plus 1 squared plus 2 squared, right? So that is how you're going to get 6. And this just means that if you will not have any other irreducible representation, so that no other inequivalent irreducible representations. I hope this is clear. So this gives you another way of trying to see what the irreducible representations of S3 are. Okay, so this was good. Now, the last bit that I wanted to say are some things called Schur's lemmas. So the first lemma is, so this says that if you have an irreducible representation D of a group G in a vector space V, and if you have a matrix A that commutes with all DGs that are in G, then A must be proportional to the identity matrix. So A has to be lambda I for some, as I write here, complex constant lambda. So let's try and prove this. So let R be an eigenvalue of V in V of this matrix A. This is an eigenvector or in V of this matrix A, and suppose this is eigenvalue lambda. Okay. Now, since D is an irreducible representation, the set of vectors, so R1, R2, up to RP, which is, R1 is DG1R and R2 is DG2R, R, and so on and so forth. RP is DGP-R. So this must span the whole of the vector space, right? So this would mean that each of the vectors can be written as a linear combination of R1 to RP. Okay, so that's clear again. So if that happens, then let's look at A over A on R1. So A of R on RA is A of DGA on R. Now remember, so what is this? So and you remember that A is going to commute with any DG, right? So A DG, sorry, let me actually use something here. So A DG I is equal to 0, so which means that A DG I is equal to DGIA. So that means we have this step. From this step, we get to this step. Now, A on R is something that we already know. This is just lambda R. Lambda is, constant thing, so you can take that out. So DGA acting on R is just RA again. Okay. So you see that this is simply, so what have we got? So we have got that all vectors in V are eigenvectors of A with the same eigenvalue lambda, and this automatically leads to the fact that A is just lambda I. Okay. For example, let's look at an example, and again, let's do our favorite thing, which is S3. So what do we do? So we start off with A being, so let's look at the 2x2 representation of S3. So so A has 4 entries: A1, A11, A12, A221, A22. Let's look at D2 of the 1, 1, 1, 2. Then this is 1, 0, 0, minus 1. What you can do is you can look at A D2 and you can look at D2A, and you equate these two guys. Okay. If you equate these two guys, what you get is that the minus A12 is equal to A12, so A12 has to be equal to 0, and A21 has to be equal to minus A21, so that also has to be 0. So at the end of the day, what we are going to get is that these two things are undetermined, but these two entries are equal to 0. So that was something that we did with one element. Now remember that A has to commute with every element. So let's look at D2 of 2, 3. So this is this particular matrix that we have out here. And again, let's do A, D2 and D2A. So we get two more things out here. And from here, it would be obvious that what we will get is, so if we equate these two, so you will get A11 is equal to A22, right? So this has to be equal to this, and this has to be equal to this. So these two, since these two have to be equal, A11 has to be equal to A12. So you see that A has to be A11 times the identity. So what we have seen in the example is that when we look at a matrix that commutes with all of these elements of with all the matrices that are representation of it, then that has to be equal to that has to be some constant multiplying the identity. So that's Schur's lemma for you. So Schur's first lemma is, let's just get back to it. So for an irreducible representation of a group G in a vector space V, if a matrix A commutes with DG for all small g in the group, then A must be proportional to the identity matrix. Okay, so that's Schur's first lemma. And then there is a second lemma. Uh, so this is so let's suppose D1 is an n1 cross n1 irreducible representation of G in an n1 dimensional vector space V1, and suppose there's D2, which is an n2 cross n2 dimension irreducible representation, which is in the n2 dimensional vector space V2. And suppose A is an n2 cross n1 dimensional matrix describing this transformation from V1 to V2. When all of the when for all of the elements G in the group, we have A D1 is equal to D2A, then one of the two things must hold. Either A has to be equal to 0, or N1 has to be equal to N2 and determinant A is not equal to 0. This essentially would mean that you can just bring this on this side, and that would mean D1 and D2 are equivalent. We will not actually go on to prove this, and I leave you with this final thing, whereby I just state another result where so the number of irreducible representations of G is going to be equal to the number of equivalence classes of G for any finite group G. So I urge you to try and look at this a little bit more. And so with these description of the Schur's lemma, Schur's lemmas actually, this is where I want to end the discussion on the group representations for finite groups. From the next lecture onwards, we will be moving on to Lie groups and Lie algebras, and we will take things forward from there. Okay, so yeah, that's it for the moment, and more to come shortly.